today we'll discuss stimulated Raman scattering. Right, so last class we sort of introduced different types of light scattering processes, and then we saw that the two main types of inelastic scattering, where the scattered photon has a different energy compared to the incident photon. The two main types of inelastic scattering are Raman and Brillouin. So we'll discuss each of those in more detail, starting today with Raman. Okay. So we'll see that this can be described as a non-parametric nonlinear process, specifically with a type 3. Okay. So last time we discussed that Raman scattering occurs due to optical phonons in the medium, right? So basically vibrations of the atoms or molecules which make up the medium, which are typically high frequency, okay? In the terahertz range, right? So we can model the interaction. So let's say you have some molecule or like an atom with some bond, right? Which again we can model sort of classically like a ball spring model, okay? And then we have some incident electromagnetic wave, and then we want to see basically the interaction of this electromagnetic wave with the vibrations of this atomic or molecular system, right? And we can, so sort of similar to in the beginning when we sort of were deriving the various susceptibilities due to the interaction of electromagnetic waves with atoms, right? Similarly, sort of here we'll do an analysis. So where, let's say, the equilibrium displacement of the bond length is some Q naught, and then there is a vibrating time varying component, right, which is Q of t. Okay? And this Q of t will couple to E of t. Okay, so again, so let's assume that this particular atomic system or molecular system has some resonant frequency of vibration, which we denote by omega r. Okay. So for the electromagnetic wave, let's sort of consider two frequencies present here. So one is a strong wave at frequency omega p, which will be, let's say, the pump. Okay. And let's say there's another weak optical wave whose frequency is slightly shifted from the pump frequency by delta omega. Okay. So yeah, just like when we were deriving the susceptibilities, right, for nonlinear optics, basically we are modeling this atomic system as a classical harmonic oscillator. Okay. So we can write again the equation of motion for this system here, right? So again, if you want to model this as a harmonic oscillator, right, like a ball spring kind of model, then you know we can write the equation of motion like this. Okay, so yeah, this this is the simple harmonic oscillator model, right? The acceleration. Then this is the damping term with some damping constant gamma. Then this is the resonant frequency, omega r square, and then this is the external force acting on the system, right? So this is the same driven simple harmonic oscillator model. Okay, so and this m is sort of the mass of the atom or molecule here, right? So in the case when we were deriving susceptibilities, this was sort of the mass of the electron, right? Because we were looking at the movement of the electron. Here we are looking at the movement of the whole atom or molecule. So this is the atomic or molecular mass of the system concerned. Okay, and basically again due to the movement of this atom, the bond will get distorted. Okay, and that will cause a dipole moment to be induced. Okay, so similar analysis to what we did, right? So you say that due to the motion, there is an induced dipole moment. Okay, which we can write as the p small p, the dipole moment per atom or molecule. Okay, so so typically, sort of the displacement is proportional to the electric field applied, right? And proportionality constant here is given by alpha, which is the atomic or molecular polarizability. Right, and this thing is basically sort of the per atom version of one, right? So you know that chi1 was the proportionality constant between the polarization induced in the medium and the electric field, right? And the polarization, you know, so polarization induced in the medium. The capital P is just the atomic or molecular density times this per atom dipole moment. Right. So this is the right. So basically now what we'll say is that so this bare system, when it's not vibrating, okay, has some polarizability alpha, okay, but when it starts vibrating and this bond starts getting distorted, basically this alpha now again becomes dependent on this vibration amplitude q, and now alpha also becomes a function of time. Okay, so what we'll say is that alpha, the polarizability, again has some equilibrium value, which is sort of the bare system without any vibrations, plus the change due to these vibrations, right, or phonon. Okay, so this is the change in polarizability per unit displacement or change in the bond length times the vibration amplitude. Okay. So basically this bond is sort of stretching and compressing, and the electron distribution is changing, right, which is causing a dipole moment to be induced. Okay, and now that is time dependent. Okay. So basically we have an oscillating dipole. Yeah?
So that vibration is induced by the electric field which we have incident on the molecule.
Yeah, so it could be, so we'll see that for the stimulated process, basically, yeah, the sort of our incident electric field is coupled to the vibration, so it excites vibration in the medium, which causes scattering into the electromagnetic field, which causes more vibrations. We'll see that how the system becomes coupled, okay? But it could be due to some other reason also. Let's say you heat it to some very high temperature and just because of thermal energy it starts vibrating, right? So this is just a general relation that if you introduce phonons or vibrations in the medium, then the polarizability starts also becoming time dependent due to the electron distribution being now time dependent. Okay. But yeah, in our case, basically, we'll see that majorly we are interested in the vibrations being excited by the electromagnetic field itself. Okay, so then we have an oscillating dipole, right? So we have an electromagnetic field here. We have an oscillating dipole. So if you have an oscillating dipole in an electric field, right? That's a system which has some energy, right? So if you recall, so energy of the dipole in an electric field is given by P dot E, right? So the energy is given by half P dot E, if you recall your basic electromagnetics, right? And here we put these brackets, which shows basically time average, because now both the electric field and the dipole moment are time varying. So we average, so this is our time average over like one optical period. Okay. And P we know is, we can write it as epsilon naught alpha E, right? So then we'll get some constant and E dot E, right? So we'll get E square here. Hopefully you can see this. So I can write U as so basically it now depends on E square. Okay. And so this will be something like, so E will vary, let's say something like cosine omega t. So this will be the average of cosine square omega t over one period, which will be something like half. Okay, so now we have an energy. Okay. So that energy, of course, depends on the displacement or the position here, right? Because sort of P depends on that. So, or alpha depends on that. So this energy depends on this displacement Q, right? So which means we have a force, right? When you have position dependent energy, you know that basically the derivative of the energy gives you a force, right? So
Sir,
Yeah.
so the relation between the force and the potential energy holds only when this one that derivative of potential energy gives force when there are only conservative forces. So how do we know that
Yeah.
here only conservative forces are into comes into play?
Uh, I mean, fundamentally, what forces are acting, right? Like sort of charges, electric fields acting on charges. So Lorentz forces, which are conservative, right? Why do you expect a non-conservative force?
There may be some friction, yeah, damping forces which are non-conservative in nature because we have taken the damping term also.
That damping we've taken separately, right? So this force basically will be the force which is acting here, the external force.
Okay, okay, sir.
Yeah, so damping is taken separately. So the rate at which these oscillations are decaying. Okay, so this force I can write as du by dq, right? So du by dq, so only term which is proportional to or depends on q here is alpha. Okay, so the force will be proportional to sort of e square, and then times this material constant, which is basically how the polarizability changes with displacement. Okay, and this is the force which is basically driving the oscillator here. Okay, so now let's assume an electric field due to the optical wave here. Again, so we're considering some strong wave at omega p and then another weak wave. So we have two, let's say we have two frequencies present here. So one is the pump with amplitude AP, okay, and the other one, let's say, is a Stokes wave with a slightly lower frequency. Right, with amplitude AS. So this is omega S is equal to omega P minus it is by omega. So the Stokes is detuned from the pump by frequency omega. Okay, and typically this omega, the detuning is much smaller than the absolute frequencies of the pump and Stokes. Right, so the frequencies are fairly close together compared to that absolute frequency. So these absolute frequencies are in hundreds of terahertz for optical waves, right? And this omega, let's say, is in the few terahertz range. Because this resonant frequency here is in that range. Of course, we'll see that the coupling is strongest when this omega will be equal to omega r. Okay, so then if we put this expression for the electric field into E square here, right? So we have E, and then we need to basically find the average of E square over one optical cycle, right? So E square, you can see, so we'll have terms like, so what terms will we have? We'll have AP square, right? but that will have a time dependence e to the I 2p omega t, right? So when we average over time, that will become 0. Similarly, as square will go as e to the I 2 omega st, average to 0. So the only terms which will not average are the slowly varying terms, right? Which are the cross terms. So AP times AS will go as e to the I omega p plus omega s. So that's also very fast varying, right? Because omega p and omega s are roughly the same. So that's also sort of varying at e to the I 2 omega p or 2 omega st, right? So only the product of this with complex conjugate. So AP AS conjugate will vary as omega p minus omega st, right? And omega s p minus omega s is a small, so that's a slowly varying quantity, right? So the only terms which will not average to 0 here are the cross terms between like this one and the complex conjugate of the Stokes, and similarly this one and the complex conjugate of the Coulomb. Okay. So what I'm saying is this. The AP AS conjugate e to the I can write it as capital KZ minus capital omega t plus complex conjugate, right? So the only average over time is a survives, which is a slowly varying one, right? And so what is capital K? The difference between the wave vectors Kp and Ks. Right, and capital omega is the difference in the frequencies, omega p minus omega s. Right, so that means that the force is just this constant times this value, right? So the right also goes like this. So now this force, which is the driving term for this harmonic oscillator, has this sort of spatial and time dependence, right? And so how do we look for solutions then, right? You know that if we drive a harmonic oscillator at a particular frequency, then the response is also at that frequency, right? So we can look for solutions. So this is the driving term, right? So then we look for solutions for Q also like this, right? And so then the task would be solving for this amplitude of the vibration Q of omega. So we just substitute this form for Q into my equation of motion. Okay, so again, so derivative of with respect to time will give me a factor of omega out in front, right? So here I have double derivative with time, so here I'll get minus omega square. And here I have a single derivative with time. I'll get an I omega. Okay, so I end up with this equation for Q of omega. Right, so the exponential terms cancel out from everywhere. Right, so you can see that the amplitude Q omega is going as AP-AS conjugate, right? So product of the fields in my pump and Stokes. So you can already start to guess that this is some sort of nonlinear process, right? Where there's some mixing going on with, between my two input waves, which is driving the atomic vibration. So this just becomes a linear equation Q of omega, right? So Q of omega I get okay. So I have some constants here, right? So of course it depends on this how the polarizability changes with the displacement, which is like a material property. There's a mass of the atom or molecule here, which is also a material property. Then it depends on the product of the fields, optical fields, and in the denominator I get some factor like what we got for the susceptibilities also, right? This omega r square minus omega square, and then this damping term. So this denominator looks similar to what we got there, right? Except now these. So there we had the resonant frequency for the electronic transition. Here we have the resonant frequency for this atomic or molecular vibration, right? And this omega is the difference in the frequencies of the two waves. Whereas in that case, we got this was the frequency of the optical wave, right? But yeah, so it's a similar form. So now that we have a solution for Q, so I erase that. So alpha, the polarizability depended on Q, right? The displacement, and the polarizability basically determined the dipole moment induced or the polarization induced in the medium, right? So we can again, similar to the case when we initially solve for susceptibilities, we'll try to write a polarization induced in the medium, and then we'll get that polarization is proportional to the product of some fields, right? And the coefficient of that we'll call some susceptibility. Okay? Similar procedure we'll follow. Yeah. Right. So this polarization capital P, I can write again the atomic density times the atomic dipole moment or the small p, then small p we know is epsilon naught alpha times E, right? And then again we write alpha as alpha naught plus d alpha by dq times q. Right, so we can split it up into two terms. So the first term will have alpha naught, right? So that term will be just proportional to E, right? So epsilon naught n alpha naught E, right? So that will be like a linear or first order polarization, right? Which is proportional to E. And then the second term here, which is now proportional to product of Q times E. Now Q also has fields, right? So this will be, second term will be proportional to higher powers in E, or the higher powers in the amplitudes of my optical waves. So that will be the nonlinear part. Right? So this linear one is just epsilon naught n alpha naught E. And then this product of Q and E will give me the nonlinear part. So now I can explicitly write the nonlinear polarization. Okay, so the nonlinear polarization is this epsilon naught n d alpha by dq, and then q times E. So q, I substitute the form for q, right? And then for E, I substitute E. Okay, so now again this will have terms going at different frequencies here. Okay, right? But we can specifically look at the term which is oscillating at the Stokes frequency, omega s. So consider the nonlinear polarization oscillating at the frequency omega s. So we'll see why we're doing this. So I mean, in the sense, we want to see how this oscillation or the response in the atomic medium acts back on my optical waves, right? So even in our usual, when we were deriving the susceptibilities, we were interested in the frequencies which couple to the optical waves, right? So similarly here. So basically, we are looking for the terms which go as some constant times which oscillate at e to the I omega st. Right. So from these terms here, we just want to pick out the terms which oscillate as e to the minus I omega s t. Okay, so from here we can see that from inspection, which term will that be? So e to the minus I omega s, right? So from Q here, I have omega, capital omega, which is omega p minus omega s, right? So if I add omega p to that, then I'll get omega s, right? So this time, so the complex conjugate of this term will be AP conjugate, and that will vary as e to the I plus omega pt, and that the product with this term will give me the term going as e to the minus I omega s. Right, same thing that we've been doing for all our nonlinear optical interactions when we look at which terms act, which nonlinear terms act back on my fields, right? Same thing here. So P of omega s right, and the spatial dependence. Okay, so the term I'll get will be AP, which is going as e to the minus I omega pt times this Q conjugate, which is going as e to the I capital omega t, right? So this Q omega has e to the I plus capital omega t. AP has e to the minus I omega pt, right? So when I take the product, I get e to the minus I omega p minus omega, which is omega s, right? I hope that's clear. And then they also have a spatial part here. So from AP, I'll get e to the I kpz, and from Q conjugate, I'll get e to the minus I capital kz. So this, so the exponential term will be, the spatial term will be e to the I kp minus capital K z. Right, but if you recall, by definition we had put this capital K as Kp minus Ks. So Kp minus capital K is just Ks. Okay, so I hope this term is clear, how we get this. Right, and then we also have a solution for Q of omega. which I erased, right? We had a solution for Q of omega which went as APAS conjugate and then those constants and then that complex denominator. So we can substitute that solution for Q of omega here. Okay, and then so we get this the nonlinear polarization at so maybe to be more specific, I should write the nonlinear polarization at frequency omega s. Okay, so this Q of omega went something like we had a d alpha by dq there, right? We had an epsilon over m, and then Q went as AP AS conjugate, which means Q conjugate will go as AP conjugate AS, and then we already have an AP here, right? So AP and we get AP conjugate AS from here, so we get mod AP square and AS. Okay, and this denominator is also coming from Q. And of course, we have this spatial part here, which goes as e to the I ks set. Okay, so does this term look familiar? Have we seen a term like this before? When we write nonlinear polarization, we get some constant into some mod A square times A.
Yes, sir.
Right? So, for example, in self-phase modulation, cross-phase modulation,
It was there, sir.
we
EP
used to get
square.
terms like this, right?
Yes.
And then the proportionality here was proportional to some chi3,
Yes, sir.
right? So it's the same thing here. So basically, we can call this proportionality constant here as some effective chi3. Okay, so recall that I can write the third order nonlinear polarization at a particular frequency omega 2 as, so we had chi3, so let's say we have two feeds E1, E2, so we used to write it like this, right? So this was something like the cross-phase modulation term, right? So the refractive index of the phase shift for omega 2 depends on the intensity of omega 1, right? And then we had this degeneracy factor here. So in this case, it will be 6 because the three frequencies involved are omega 1 minus omega 1 and omega 2. So 6 permutations, right? So this form is exactly like this, right? You have mod A square and some other A here. So we can define a Raman nonlinear susceptibility Okay, so basically just take this form and then these constants will equate to some chi3. Right, so we write P of omega s as some 6 epsilon naught. Now here we have chi3 Raman. Okay, so we just write this like this and define a Raman nonlinear susceptibility chi3 sub r. Right, so this is basically mod of EP square ES. Right. So EP went as e to the I kpz, ES went as e to the I ksz, so that's why we have this e to the I ksz there. And this chi3 Raman at omega s, right? If I want to write it explicitly, recall it's the chi3 at frequency omega s. The three contributing frequencies are omega p, minus omega p, and omega s. Right? Just like similar to a cross phase modulation term. Okay, so from here I can write chi3 Raman at omega s, which is same as omega p minus this detuning. Okay, so it looks sort of similar to the chi3 that we derived for electronic nonlinearities, right? Constants are different because it's a different process. So here now, how the polarizability varies with displacement, that factors in here. Of course, we have the atomic density or molecular density and the atomic or molecular mass, and then the similar denominator term with the detuning. But now the frequencies appearing here are so this capital omega, the detuning between pump and Stokes, and this capital omega is the Raman frequency. Okay, so first thing to note again, this due to this thing, right? It's a complex quantity. It has both real and imaginary parts. Okay, which is sort of the same case as we had for the electronic susceptibilities also, and then in some particular limits we saw that we can approximate them as purely real, right? And then we saw that the real part of susceptibility gives you parametric processes, right? And imaginary part gives you non-parametric processes. The only examples we've seen so far are like nonlinear absorption, two-photon absorption, for example. Similar is the case here, right? You have real and imaginary part. So, like a real part, this real part will give me a nonlinear phase shift, just like for the actual chi3 case, right? For the electronic nonlinearity, and the imaginary part we'll see will give me gain or loss. Okay, so For the electronic part, the only case we saw was loss, like nonlinear absorption was basically giving us loss. Here we'll see that it can either give us gain or loss depending on this frequency.
Sir, in this derivation, we have taken polarization has only the linear term, but the interaction between the molecule and the light field produces the nonlinear term, gives the nonlinearity actually.
Yeah, so this is the nonlinear term, right?
So initially, we have taken the polarization to be only linear.
Yeah,
when
so
we
we
have
start. So it's something like we start from. So remember,
epsilon.
like, we can write say polarization like this, epsilon naught chi e,
Yes, sir.
right? And then you can say, okay, my chi has the first order term is a constant term, but I could have higher order terms, right? So I could have, let's say, chi 2e plus pi 3e square, right?
Yes, sir.
And the higher order terms will give me the
Nonlinearity.
nonlinear term. That's what we did, right? So here, alpha we had.
Hello.
This is what is giving me the nonlinear term.
Sir, the connection is lost, I think.
Is it back?
Uh, yes, sir. Now it is back.
Yeah. So, right. So basically, that's what we did, and then the nonlinear term is giving me the Raman couple.
So the nonlinear terms and the linear terms are in the expression alpha actually, and that we have taken to be time varying due to the interaction between the light and the.
Yeah. Yeah. So the constant. I mean, so this bond with this atomic or molecular bond. Let's say if it's not vibrating, it's at some rest, so that it has some polarizability at when it is not vibrating. That's alpha naught. That gives me the usual linear susceptibility. Right? But when it starts vibrating and the vibrations coupled to the field, that's what is giving me the nonlinear susceptibility.
Okay, sir.
Okay, so let's now just focus on this susceptibility. Right. So now basically we can use this susceptibility and do the same standard analysis that we do for any nonlinear optical interaction, right? So we have some chi 3. So now, for example, we can write coupled amplitude.
Hello. So I think connection is again lost.
Hello? Hello? Is the connection
Yes, sir.
okay?
Yes, sir. Yes, sir. Now fine.
And yeah, in the
Yes,
middle.
sir.
Yeah, so what I was saying is the susceptibility here depends on the detuning between or the difference in the frequency between these two waves, right? Whereas the usual electronic susceptibilities depend on the absolute frequency of the optical wave, right? But here it depends on the difference in the frequency of the two waves. So, of course, the coupling will be strongest when this difference in the frequencies is close to the natural frequency or the Raman frequency of the material. Okay, so let's look at frequencies which are close to the Raman frequency, right? So omega close to omega r, right? So if omega is close to omega r, then omega r square minus omega square, which I can write as omega r plus omega r minus omega, I can approximate as 2 omega r minus omega. Okay, so I say omega is close to omega r, right? So omega r plus omega is basically 2 omega r, and only the difference. So this difference in the squares now goes as just the difference. So it's some sort of linearization, right? And this omega r minus omega, right? So omega r minus omega. So what is omega r? Omega is sort of it's a material constant, right, for a given material, the natural frequency of vibration. And then omega we know I can write it as omega p minus omega s, right? So okay, so let me just write it. I can write this as omega p right? Omega r minus omega, I can write it as omega p minus omega p minus omega r. Okay, so omega p minus omega is just the Stokes frequency, and this omega p minus omega r I call the Stokes resonant frequency. Okay, so this thing is the Stokes is equal to this. Right, so that's the Stokes resonant frequency. So when the Stokes is exactly the Raman shift away from the pump, we'll see that that's when the effect or the coupling will be maximum. So that's why it's called the Stokes resonant frequency. But in general, the Stokes frequency could be slightly away from that. Right? So this omega minus omega term is basically the actual Stokes frequency minus the Stokes resonance frequency.
Can you explain again Stokes resonant frequency?
So this is, so for a given pump frequency, this is again some constant frequency, right? Omega p minus omega r. So for a given pump frequency and a given material, I can define this frequency, right? And I call that as the resonant. So basically, exactly a Raman shift away from my pump, I'm calling that as the Stokes resonant frequency, because we'll see that the Raman coupling will be maximum there. Okay. And so basically here what I'm doing, let's say I'm sending in a Stokes wave with frequency omega s, and I'm varying that frequency. Okay. So
I have a confusion regarding resonant frequency and Raman frequency. So WR is omega of r is the resonant frequency.
Okay, so this small omega is the optical frequency, right? Whereas this capital omega is the frequency of the vibration.
Vibration.
Right?
Yeah. Okay.
So this capital omega are low frequencies, right? Few terahertz, whereas these omega are optical frequencies at hundreds of terahertz, right? So this omega SR is omega p minus this capital omega r, which is again an optical frequency. So I'm saying if you send in a Stokes wave, which is at this frequency, then it will couple maximum with the pump due to the Raman coupling, right? Okay. But in general, I could have any Stokes frequency omega s, right? So how much that Stokes frequency is away from this resonance frequency is basically this quantity.
Okay, sir.
Right, so this is basically some delta omega s, right? So this resonance cost, we also call it sometimes a peak Stokes frequency, because we'll see that the gain maximum or the peak of the gain will occur at a Stokes frequency equal to omega SR. Okay, and how far detuned from that peak I am is basically delta omega S. Okay, and then for this, okay, so this omega r square minus omega square, I can basically write it as 2 omega r times delta omega s, right, from here. So that's one approximation I make here. And then this second one is this complex term, which is 2i omega gamma. I replace the capital omega by capital omega. Okay, so you can see that this first term omega r square minus omega r has 2 omega r here. Then the second term will also have 2 omega r here. So I can take 2 omega r constant from both of them, and basically write my susceptibility now as so I get a 2 omega r from there, so this becomes 12 m omega r.
So the connection is again lost, I think.
Is the connection back?
Yes, sir.
Raman susceptibility at a Stokes depends on basically the detuning of the Stokes frequency from this peak frequency.
It is again lost.
What is happening here? Okay. So the Raman susceptibility at a particular Stokes frequency depends on basically how far that Stokes frequency is from the peak. Right? This depends on delta. So you can see this is some kind of Lorentzian line shape, right? This should be familiar, like 1 over detuning plus I gamma. This is a Lorentzian line shape which you must have seen in many other places. Right, so now we have a simplified form here, and we can easily see what are the real and imaginary parts. Right? So right, so the real part just take the real part of this. in the imaginary part. Okay, so now you can see explicitly that the real and imaginary parts are basically they have this 1 over delta omega square plus gamma square, which is the Lorentzian function. Right, so these are very familiar line shapes, right? So how do they look? So if I plot as a function of delta omega s, how would the imaginary part look?
So in the denominator, it will be delta omega square.
Yeah. So yeah, this is just a Lorentzian function, right? So forget about the negative sign. Let's say we are plotting the magnitude, then it looks like this. Right, so this is the magnitude of the imaginary part. Lorentzian, right, with a width, right, so this full width half max here is 2 gamma. And how would the real part look? Right, so, and this zero detuning is basically where the Stokes frequency is equal to the Stokes resonant frequency, which is omega p minus the Raman frequency. That's where the
So one time it will be positive, one time it will be negative, sir. Real part.
yeah. So the real part goes as delta omega by delta omega square plus gamma square.
Positive,
So,
it will go. From zero crossing, it will go.
so because there's a negative sign, yeah. So for negative, it's negative, right? So it looks like this.
It will go up, sir. Then bend. Yes.
Right, so very familiar line shapes. So, right, typically, even like in a linear medium, if you have some absorption resonance like this, where the absorption goes like that, then the refractive index goes like that. Right? Similar, very similar. Okay. So you can see basically that there's a Raman resonance here at a frequency, Stokes frequency, which is Raman shifted, downshifted from the pump, right? And the Raman line width is given by this gamma, right? Which was basically the damping constant of this vibration. So that's basically how fast these vibrations are decaying, or basically how long the phonon lives in the medium, right? That is what determines gamma, or the width of this. Okay, so that's at the Stokes side, or the lower frequency side from the pump, right? So, but if you remember our discussion in the last class, we have scattering on both sides, right? Stokes and anti-Stokes, right? So we can also look at frequencies which are higher than the pump, which will be the anti-Stokes. Okay, let's see how those look. So we'll have to go back to the original expression for the Raman nonlinearity in terms of the capital omega, the detuning frequencies, right? And then, so now what I'm saying is instead of Stokes here, I have a frequency which is higher than the pump. So it's very similar. Yeah, just right. So here we had chi3, the Raman. Right, where omega here is omega p minus the other wave, right? So here in this case, okay, maybe I'll just denote this as some, let's say omega prime, right? So omega prime was omega p minus the other wave. So in the Stokes case, it was omega s. Here, if the other wave is omega a, then this is minus omega, right? So this sign will flip here. Okay. So in terms of omega, this will become minus. Okay, I hope that's clear. Right, and now we look at again frequencies which are close to the Raman resonance. So for the Stokes, we were looking at frequencies which are downshifted from the pump, and that downshift is close to the Raman shift. Here we are looking at frequencies which are upshifted from the pump, and that shift is close to the Raman frequency. Right. So again, so to look near anti-Stokes resonance, basically omega close to omega r. So same thing here. So omega r square minus omega square, I can approximate it as 2 omega r minus omega. Okay, which you can write it as 2 omega r omega a r minus omega a. Okay, so this is omega p plus omega. This is omega p plus omega r, which is the anti-Stokes resonant frequency. Or peak. Okay, so omega AR minus A is minus delta omega A. Okay? So delta omega A is the detuning from the resonance, which is omega A minus omega AR. So we get a minus sign here compared to the Stokes. Stokes we just had delta omega S. Right, and again this 2i omega gamma is approximated as 2i omega r gamma. Right, so we substitute again this and this into here. So again, same thing, we get 2R common, and then we'll get a factor of delta omega A plus I gamma. So for the anti-Stokes resonance, okay, it's the same form. Same form as the Stokes, except you have a minus sign here. But rest of the expression is exactly the same for the Stokes. Just there is a minus sign. So when you take the real and imaginary parts, basically there's just a sign flip, right? So if the imaginary part of at the Stokes looks like this, then at the anti-Stokes it will look like that, right? And similarly for the real part, if one looks like this, the other one looks like that. So there is a sign flip. Okay, so now we can try to plot this Raman susceptibility over the whole range, right? From the Stokes across the pump to the anti-Stokes, how it looks. Now. Okay, so let's plot the susceptibility. So centered, so we are on the pump frequency of the center. Okay. And then if we go Raman shift down from the pump frequency, you get the Stokes resonant frequency, right? So this is omega r. And then if you go higher by a Raman shift, then we get the anti-Stokes resonant frequency. Right? So axis is omega. Right, so the imaginary part, how does it look? So for Stokes, it was negative. Right, so it looks like this. Right, so the peak occurs at the Stokes resonance frequency, and the width is proportional to this gamma. On the anti-Stokes side, the sign flips. Right, so this is the imaginary part. same thing here with this. Right? And the real part looks like that. Okay, so that how it looks on both sides of the pump. Right, so you can see that the values of the susceptibility are opposite in sign at the Stokes and anti-Stokes side. So we'll see that basically what happens is, so the imaginary part gives a gain or loss, and turns out that it gives gain for the Stokes and loss for the anti-Stokes. Okay, and the real part gives rise to something like a refractive index, right? Except now the refractive index is dependent on pump intensity, right? So you can see that the shape of how the refractive index varies is now opposite for around the Stokes and the anti-Stokes, and the slope is opposite. In the Stokes case, the slope is increasing. In the anti-Stokes, the slope is decreasing, right? So if you look at the group index, so Ng, which goes as dN by d omega, that is positive for the anti-Stokes. So this gives rise to slow light, which means the wave here travels slower. The photons here travel slower than what they would without the pump, right? Because your group index is now higher. You have a positive slope which adds to your group index, so the group velocity goes down. Okay. And here you get the opposite effect, or fast light. Okay, so on the Stokes side you get gain or amplification along with slow light. On the anti-Stokes you get loss or attenuation along with fast. So let's look at some typical values. So what is this Raman shift here? If I look at silicon, this Raman shift, omega r is the angular frequency, right? So omega r by 2 pi is the actual frequency in hertz. That's about 15 terahertz for silicon. Okay. Sometimes this Raman shift is measured in centimeter inverse, especially in areas related to chemistry and materials analysis, where they characterize materials using this Raman spectroscopy. Usually they measure the Raman shift in centimeter inverse. Okay. So in centimeter inverse it is that 520 centimeter inverse, right? which is basically you divide this by C. Right, so this this quantity in centimeter inverse is basically omega r divided by 2 pi c. You can see it has units of 1 over length or 1 over wavelength. Okay. And then this damping constant for the vibrations of the phonons, that is about 50 gigahertz. Okay, so typically you can see that the line width here is much smaller than the Raman shift. So gamma is much smaller than omega. So you can see here it's almost a factor of 1,000. Right. So gamma is something like the inverse. So basically, gamma is how fast these vibrations are decaying, right? Which is basically you excite a vibration and see how fast it decays, right? So it's the inverse of the lifetime of the phonon. Right. So if you have a longer lived phonon, then this will be smaller. Gamma will be smaller, and the line width will be narrower. If the phonon decays really fast, then this line width is broader. So gamma is basically here. So gamma is inverse of phonon lifetime, right? And omega is basically the phonon frequency, or proportional to the energy of the phonon, h cross omega. Right, and then if you look at, for example, diamond, which is carbon lattice, this Raman shift is very big, 40 terahertz. Okay, and so in centimeter inverse is 1332. And gamma is about 30 gigahertz. Okay, so both silicon and diamond are crystalline materials, right? So they have a very well defined crystal structure. So they have very well defined these optical phonon modes. So the modes of vibration are very well defined. It's a crystalline structure. So that's why this resonance is really well defined. So and they are at very high frequencies, and the line width is much small, very small compared to the, which means what? That the phonon lifetime is long, right? So the vibration, once you excite it, stays for some time before it decays in crystalline materials, right? Because the material is, right, it's very ordered and nice, so there is the phonon lives for a long time, and because the atoms are all bonded close together covalently, right? So the vibration also happening at a high frequency. So we can contrast this with an amorphous material like glass, silica. Right? So these are crystalline materials. So on the other hand, silica, glass or SiO2, from which optical fibers are made, right? So that's an amorphous material, which means it doesn't have a regular crystal structure, right? So sort of the molecules are distributed randomly across the medium, right? And so you can imagine basically what happens is that you get many different, so depending on how the bonds are distributed, right? So for each particular arrangement of the atoms and the bonds, you get a particular vibration mode, right? So for these crystalline materials, basically that's a very well-defined mode. But for an amorphous material, you have various different kinds of arrangements sort of smeared all together, averaged over the material. So what happens is you have various different modes which are at different frequencies, right? Sort of smeared over together, right? So instead of a nice Lorentzian with a narrow line width, basically what you can imagine it's sort of like many different Lorentzians at different places and different line widths, right? All sort of averaged together. So the whole thing will look much more complicated. So for glass, so if you plot the sort of imaginary part of the Raman susceptibility, okay, it doesn't look like a nice Lorentzian anymore. So numbers here. So this axis is the detuning in terahertz. So omega p minus omega s, basically the difference in the pump and stokes. Or equivalently, so let's say this is the mod, or if you're looking on the anti-Stokes side, it's omega p minus omega a minus omega p. Okay, so it looks very complicated like this. It doesn't look like a nice Lorentzian. And also you can see it's very wide, right? So the line width, so the peak occurs around, so this is 15 terahertz. Right? There's another sort of slightly smaller peak at around 12 terahertz. But you can see that it's very broad, right? So the width here is almost like 10 terahertz, right? So basically in amorphous materials, the resonance gets broadened out quite a bit. Okay, so what we are saying here that for amorphous materials, the line width, sort of effective line width, or the effective line width becomes comparable to omega. Right, so for this case, the line width is much smaller than the resonance frequency, whereas here it becomes comparable to the resonant frequencies. Right, which means, so on average, the phonons are very short-lived because there are lots of defects in the medium, right, which decay the phonon very quickly. Okay, so yeah, to explicitly tell you, so basically, if you have so this if you have a sort of Lorentzian shaped peak in frequency domain, right? So this is chi 3 Raman omega, right? It looks like that. Then if you take the Fourier transform and go to the time domain, right? So the Fourier transform for the Lorentzian looks like a damped sinusoid, okay, where the oscillation frequency of this sinusoid is basically omega r, which is the peak of the Lorentzian, right? And the time scale over which it decays, the exponential decay, that time, so if this width is gamma, 2 gamma, then this exponential decay time scale is proportional to the inverse of gamma. So that's the lifetime. Okay. So, so this is sort of like the Raman response function in time domain, right? And this is the response to the frequency, the susceptibility, right? So for this Lorentzian shape here, right? So this is proportional to 1 over omega minus omega r square plus gamma square. You can get this time domain response function, the Raman response function, which is called HR of t. Right, so HR of t I can write like an exponentially decaying function e to the minus t over tau phonon times the sinusoidal function t over tau r. Right? So omega r is basically 1 over tau r, right? And this gamma is basically 1 over tau phonon, which is the phonon lifetime. Right? So yeah, so gamma is 1 over tau phonon. This is 1 over the Raman oscillation time period. Okay, or in other words, what I'm saying is that remember again in the beginning of the course we had discussed sort of frequency domain and time domain representations, right, for the nonlinear susceptibility and nonlinear polarization, right? So what we just wrote was there is a third order polarization, effective third order polarization that I can write due to the Raman interaction. Let's say at the Stokes frequency, right? Something like this. Right, so this is the frequency domain representation. But equivalently, I can write a time domain representation. Right, so I can write the Stokes polarization, or the third order polarization at the Stokes as a function of time. Right? So basically the Stokes polarization at the current time t depends on the pump fields for all times previous to the current time, which we convolve with the Raman response function. Okay? So remember in the beginning of the course we wrote like this frequency domain representation and then the time domain representation where we had a response function, and the Fourier transform of the response function was the susceptibility, the frequency domain. Same thing here, right? So there is a Raman response function, whose Fourier transform is the Raman susceptibility. Right. So in the electronic case, typically this response function was almost instantaneous, right? Especially if we worked far away from the band gap in the Klein and symmetry limit. So basically, this response function for the electronic susceptibilities were basically a delta function, right? So basically, this was instantaneous, right? And equivalently in the frequency domain, all these susceptibilities were frequency independent and real quantities, right? In the Raman case, you can see explicitly here, of course, there are time scales involved. So HR of t is not a delta function, right? It has some particular response function, and because of that, the susceptibility has both real and imaginary parts, right? So this kind of simple model you can do for crystalline materials where the Raman resonance is very well defined. But for silica, as I drew, it was very complicated, right? So basically, you try to model it with a more complicated Raman response function, right? So you just don't take a decaling sinusoid. You have to take more complicated functions to try to model that kind of thing. So Agarwal talks a little bit about that if you're interested. Because silica is a very important material, right? Optical fibers and all sorts of optical elements we make out of silica. So to understand the Raman response in silica has been an important topic for a long time. Okay, so maybe we'll stop here. And next time we'll sort of, starting from the susceptibility and nonlinear polarization, we can again write the canonical propagation equations, right? Similar to what we've been doing, because we've now defined the susceptibility and nonlinear polarization. So straightforward to write canonical propagation equations and get sort of coupled amplitude equations between the pumps and Stokes, or pump and anti-Stokes. And we can explicitly see how they propagate, how the Stokes gets amplified and the anti-Stokes get attenuated, etc.
Sir?
Yeah?
Sir, to audit a course, we have to send a mail to you regarding that to get your permission.
No, I think basically you have to do sort of from your ERP.
Yeah, that I have done, but sometimes
You log in and you just put in a request, so the request will automatically come to me, and then
okay, sir.
I can approve it from my side. So yeah, if you've done it from your side, then it should appear in my system also.
Okay, sir.
So I'll just wait till 26th, which is the last day, and then see all the requests.
Sir, do we have to consider the noise also because of this stimulated process in this?
So stimulated process here, sort of we're considering two input waves, right?
Yes, sir.
Pump is a strong wave, and then Stokes or anti-Stokes is a weak wave. Now that weak wave could either be like a actual input wave we are sending, or it could just be noise.
Okay, sir.
Right? So for example, you could have noise present in the medium at all these frequencies. The noise at the Raman frequencies will get amplified more than the noise at the other frequencies. Right?
Okay, sir.
Yeah.
So here previously, we won't going to consider any spontaneous noise or phone because of spontaneous phonon present in the system. Nothing, right?
Yeah, I'm not. I mean, just because of sort of paucity of time and
Okay.
we can cover in a course. So to actually consider the spontaneous and noise processes, you have to go sort of to quantum treatment, right? Yeah, it becomes a little bit more involved. Yeah, for the course, we'll just stick to stimulated and not consider spontaneous and noise processes. But there are discussions of that, I think, both in Boyd and Agarwal. If you
Yes, sir.
want to know. Yeah.
Thank you, sir.